Hi, Steve,
Hi,
and
Kyle.
welcome everyone. Welcome everyone to NonSequitur. We're glad you're with us today. Steve, everything okay your way?
Kyle. Everything fine, Kyle?
You have no idea what
You
I'm
look
doing right now, do you?
no, but you look really good, Kyle. You look
Good.
fabulous.
I'm glad you don't know. I'm sure someone out there has put together what's going on right now. And if you haven't, you're in for a really good treat tonight. We're going to go through the world of ASMR. Do you know what that is, Steve?
I do. I actually I like ASMR.
Oh, of course you would.
Where's that
Let's
word?
bring us back then.
Autonomous sensory meridian response.
Okay, Cartoon Kyle and Steve, we'll say goodbye to them. And I
Hi.
started that off today. Yes, we are real. We are real. We are going to kind of dive in, first of all, to a world that, thanks to Jammy, and that I have been trying to get in contact with someone from this community. I think that I have pretty well sussed out somebody to come on and actually talk about this in depth. But there's a strange subculture to ASMR that I want to kind of dive into a little bit today. And this is my new favorite thing on the planet. I didn't know about this until today. I hope that you who are watching have not seen this in great detail, because if you have not, then you're in for a treat, because this is epic and gold and just everything. It's my new obsession. What First Amendment
Really?
auditors were, yes, this is taking the place. Okay. First of all, let's start out by, for those of you who don't know, let's talk about what ASMR actually is. And there's a diagram on this next slide that we'll pull up. Basically, it's that you experience, it's an experience characterized by a static-like or a tingling sensation on the skin that typically begins on the scalp and moves down the back of the neck and upper spine. So, what does that mean? Well, if any of you, which I'm sure many of you have been, if you are in a situation where you are, let's say, about to get it on, right? And that kind of dirty talk that goes on in the, you'll see what I'm talking about here in a second. You'll understand. This will all make sense, I promise you, okay? But there's that,
Can't wait.
that tingling kind of conversation that you have that is really going to be prevalent in this. And there's no real way for me to do it justice other than to let someone who actually does this speak to it. So we're going to start with a video. We're going to do a couple of seconds of, I've got 6 videos that I want to do like 5 to 10 seconds of each video with. So, Dave, if you will, please, let's bring up the individual that will introduce us to ASMR as a whole.
Rapunzel. ASMR. I decided to do another old school video.
Oh God, that's hot.
This is inspired by what I saw recently.
Okay, Dave. Let's move on to yeah.
Like this rhythmic.
Let's go with the for those like myself who would like to hear a guy do it. Let's go with the guy who is going to wash our face for us.
This
Okay,
is
so if you ever,
is this gonna remind me of my days in Boy Scouts where my scoutmaster was just like, "Just let it happen, Steve. Just let it happen."
no, this answers the question. This answers the question. If you ever wanted to get a face washing simulation, Okay.
Oh God.
This gentleman right here will help you out with that. So Dave, let's get our face washed.
Hello. I haven't seen you in a while. So tonight I wanted to do something a little different that I haven't tried before.
Okay.
It's going to be ear
Ooh.
to ear.
Ooh.
And I
Be
would
gentle.
like to give you a sex massage and also to clean your face.
Oh God.
Now, I'm not a
You're so good at this.
Oh.
Oh.
But
Oh, you're so good at this.
just try
You're
to
so
do
good
these
at this.
sounds
Yes.
and try to
Yes.
relax
Yes.
and try to do it as quiet as possible.
Oh, okay, Dave. Let's go to the next one before I die. I'm about to piss myself right now. Let's go to the next one, Dave.
Oh, this is so wrong on so many levels.
Actually, Dave, go to the lollipop one. We won't go to all of them, but
There's two of
Go
them,
to
but
the-
which one?
yeah.
Which one do you want?
the long rainbow one.
The long rainbow.
The last one that I sent you that said start at from the beginning to the first 5 seconds and then start at 3 minutes, I believe. This is the one that you have to see, ladies and gentlemen, because if you want to know what this is, what I think this is really about.
Oh
Here
God,
you
this is
go.
gonna trigger people. This is gonna so trigger people. Damn.
Welcome to my skeleton lair.
Actually, I think that's not the right one.
Yeah, that is the right one. That's the right one. All right, now go
Okay.
to 3 minutes.
Rainbows and everything. It's so rainbow and pretty. Pretty things aren't allowed in my deep, dark skeleton.
Okay, you got. We'll stop it right there so that we don't.
She's got like
we
alien
don't-
eyes.
we don't
like,
go
like
too
she's
far.
related like Grays or something. Those eyes.
I
That
don't
was
know.
about to get really suggestive.
Yeah.
Demonetized. Just go with that. It's gonna
Right,
get
yeah.
really demonetized.
So
Leave it at that.
I encourage you all to go out and experience the world of ASMR. There are several videos on there. Now there are some on there that and the person that I'm trying to get on here, it's a different version. It's not this kind of like overly sexualized and innuendo type thing. There are like it'll help you go to sleep. It puts you into some kind of like calm state. There are ones who take it seriously and do a different kind, I think. But there is this world of people who just go crazy with it. There's a lice checking simulation, so it's like you're sitting in front of a nurse at school while she checks you for lice. There's a salon simulation where you go and you're staring at a wall and there's somebody talking to you like you're getting your hair cut. And you just hear like clip clip and then clip clip, and it's amazing. It's absolutely amazing. What we need is a flat Earth simulation where we are watching the debate, but through our own point of view.
No, from the point of view of the flat earther or something. But I'm really surprised that ASMR is something relatively new to you. Actually, it's got a cult-like following.
This version is, yes, but these people have millions of people that follow them. I mean, it's amazing. It's amazing. Okay, so enough with that. Let's get to the star of the show. There he is, the man, the myth, the legend, Dr. John Croon. Welcome back.
Hey guys, what's up?
Get a little fanfare.
Yeah,
Fanfare. How goes it, sir?
goes well. I'd like to give a shout out to my students. I got our school T-shirt on here. We got the Hayfield Hawks. Some of you guys may have tuned in tonight. Come check it out. Thanks for watching.
Excellent. Get that extra credit, right?
Yeah, absolutely.
You were with us, or you were with Steve on Sunday, and we talked about what happened before the Big Bang. I'm sure Steve did a great job of explaining to everybody that it does make sense to ask that question, and that yes, there was a brief period of time before the Big Bang. I heard nothing but good things. So
Let him think what he wants. It's okay.
Yeah.
It's okay. Just talk like this the entire.
Don't do that, Steve. That's what nightmares are made of.
I'm telling you, it's creepy, isn't it? It's so creepy.
That's what nightmares are made of. So
I make a fortune at it.
we are going to pick up kind of where we left off last time you were here. Last time you were here with us, we were going through some of the an intro, I guess, to exoplanets in detail, and we briefly touched on the Drake equation. Do you want to kind of take a few minutes and introduce yourself, tell everybody who you are, what you do, and then we can just roll right into life on other planets?
Yeah, should I also include a very brief summary of the last one, or is it incumbent upon them to go watch it?
Okay. Well, both.
Both.
We'll do both.
Definitely watch the show.
Brief summation, and then go watch the other video, guys.
Okay, so Dr. John Croon, got my bachelor's in physics in 2010, master's in 2013, PhD in 2016 in astrophysics, focusing on analytical solutions for electron transport problems using differential equations and closed-form solutions. I have 4, maybe going on 5 first authorship publications on my models of various astrophysical quandaries. After that, I was an NRC postdoc for 2 years, and I'm currently teaching physics at a local high school. Last time we talked was, I believe, August 16th, right, Kyle? I think that was it, yeah. That was the first exoplanet show where we went through in great detail, if my reviews of the show are accurate, the physical principles that are relevant for actually ferreting out the facts and the data and the evidence for exoplanets in our galactic neighborhood. We talked about Kepler data, how there are thousands upon thousands of confirmed exoplanets. We talked about how this population of confirmed exoplanets is divided into gas giants that are called hot Jupiters, and those are by and large inhospitable to life. We talked about super Terrans and terrestrial planets that are similar in size and composition to Earth, as well as planets that are sub-Terrans, that are smaller than Earth, such as Mercury and possibly Mars. We spent a good deal of time talking about how we know what we know, and we talked about, I think, 1 or maybe 2 exoplanets. And then after that, I introduced the idea of this so-called Drake equation, which attempts to model the total number of intelligent civilizations in our galaxy by use of the Drake equation. And we looked at some models, parameter input examples that I drafted up, and I gave you the URL, the website, so you guys can go and play around with it on your own. And I think the most interesting take-home message for the Drake equation was that so if any term in that equation is 0 exactly, then there's no life in the galaxy. But we know for a fact that it cannot be 0 because we exist. And so then it's just a matter of finding out, is there 1, 2, 100, 1,000, 10,000 intelligent communicating civilizations on planets elsewhere in our galaxy? And that's where
we, Dr. Croon? I don't know if you watched last night's episode, but we may not exist. That answer might be actually 0.
And some people might even argue that we're not even intelligent, so we wouldn't even qualify for that because we're looking for intelligent civilization. Yeah, so.
Well, sure. I didn't catch last night's. I'm a true fan, but I didn't catch last night's episode. I'm gonna watch
simulation
it in a couple
theory.
Days. Oh gosh,
we could be living in a simulation.
Oh, I know what you're talking about. I don't know if I want to watch that one. Only if I have my oven mitts handy.
You sound triggered.
It was good. No,
oh man,
good. It was good.
Do you we explored it in a good way, in a playful almost way. We were taking the idea that if the laws of physics and everything that we know about science is true, how would that be applied to if we were living in a simulation? So we kind of went through, how would you be able to figure out what would the ethical implications be, that sort of thing. So, yeah, it was fascinating.
Sure.
You won't be triggered.
Yeah,
Don't worry.
I'll check it out.
You got angry there, didn't you, Steve? You got really angry.
He did. I think there's a little kind of
No, because I had flashbacks to some of the various flat Earth shows. There's the one with SI, the one with Jaren, and their lack of substance.
Well, I mean,
I thought you were going to say that you're having flashbacks like Westworld. You know what I mean? Where how they have flashbacks, and if you're having flashbacks to a simulation, you need to tell us, Dr. Croon. You could be humanity's only hope.
The flat earthers will invoke simulation theory, but I mean, there is a legit argument for simulation theory. I mean, there's an actual paper on it, but no. Well, I mean, there is an argument. It doesn't have to be a convincing argument. It's not even. I don't think it's convincing. It certainly doesn't convince me. But it is a legitimate scientific argument. I mean, think about it. They're literally testing this. Scientists are testing that hypothesis as we speak using lasers right now. So they are.
Can we get them to do something more productive?
So, I don't know how they're getting grants for it, so somebody wants to know.
Sure.
Well, yeah, so when
let's
you say
talk about
lasers,
exoplanets.
You're talking about the double slit experience. Yeah, exoplanet time, I guess. Yeah.
Yeah.
Kyle, go ahead and usher us in. What do you want? What's on your mind in terms? Where do you want me to start?
Well, I figured that we, Dave, we can pull Dr. Croon and sandwich him in between Steve and I down here on host row, and we'll go to slide 20. I believe we said we were going to start with. And
stay on the title slide for a minute, for a little bit.
Yeah, I'm looking forward to hearing like a little bit more about some of these specific exoplanets and the the instruments that are going to be looking for them and how they are going to, because there's the James Webb that's going up soon, and that's supposed to be a game changer. And I'm interested to hear like how those instruments are going to be the defining factor that kind of launches us into that new age of space exploration.
Oh yeah, sure. So yeah, let's keep it on this slide for a few minutes. I'm gonna have I have just a few comments I'd like to make that are important for us to all keep in mind before I launch us into looking at specific exoplanets and water worlds and possible Earth 2.0. Sound good?
Yep.
Absolutely.
All right. So the sort of elephant in the room is that searching for exoplanets is at least in a large part motivated by the search for life. So we don't just want to find a hunk of rock that we could study, or even a hunk of rock that we might move into one day in a century or two or more. This is my opinion. I believe that we, the people, we, the human race, are very curious and interested in finding not just a habitable planet in our galactic neighborhood, but one that actually hosts some form of complex life. Multicellular would be great. Some form of intelligence would be mind-blowing, of course. And so we talked about the Drake equation. But one thing that I would ask everyone to keep in mind is that when we talk about habitability and the habitable zone, we're going to be talking a lot about the habitable zone and planets in the habitable zone and whatnot. If you were to calculate Earth's habitability based solely on its distance from the sun and the sun's luminosity, then you would get an average global temperature that is much colder than it really is. We get an average temperature of like, what is it? Like negative 10 Celsius, which is like pretty cold, a lot colder than we really see. So when you realize that there's another contribution that greatly determines the planet's average temperature is the presence of greenhouse gases. So when you recalculate Earth's average global temperature, and you take into account Earth's albedo, which is its reflectivity, and its distance from the sun, and the sun's luminosity, and you also tack on top of that the amount of carbon dioxide and methane and other greenhouse gases in its atmosphere, then you arrive at an average global temperature that's what we observe. So sure, the poles are pretty cold, the Arctic, the regions are cold, then you have the tropics, which are always warm, like year round, and you get an average global temperature that's 54 degrees Fahrenheit, if I remember correctly. So that's something that we should keep in mind. Are you guys hearing that? There's like some. It sounds like I'm by a highway, or is that just me?
No, you sound good to us.
Okay, cool. There's something weird on my end, but it's okay. One other thing I want to ask the audience to keep in mind is that life may end up being discovered on a moon around another planet that's itself not in the habitable zone. For example, Jupiter's moon Europa is most certainly outside of the habitable zone for our solar system. Jupiter itself, it's pretty far away. It's over 5 times farther from the sun than we are. And so it receives 1/25th of the solar flux that Earth does. So you wouldn't want to look for life there if you just go by that criteria. But gravitational interactions between Jupiter and some of the other Galilean moons allow for a vast ocean of liquid water, we believe, underneath an ice crust of the planet Europa, which is one of Jupiter's Galilean moons. So you might want to cast a wider net and not be too restrictive in the criteria that you use to look for habitable worlds, planets, and moons of those planets and other solar systems. All right. I'm going to ask Dave that we go to slide 20 now. All right, so I have this. I borrowed this from Wikipedia. You could do the same searches and find exoplanets. Some of the top, I think this was like the top 10 or 20 exoplanets, broken down into, in this case, exoplanets in what's called the conservative habitable zone, HZ habitable zone, where you're not being too stringent on the restrictions. So if you look at the top there, you see Earth. That's us. Sol. That's our star, the sun. And the star type is a G25. Its mass, the mass of our sun is 1 solar mass. We use the sun's mass as a sort of a reference point for other stars we'll encounter in the galaxy. And the radius of the... I'm sorry. That was a mass of the Earth when it has a circle with a plus sign in it. That's the mass of the Earth. And the radius of the Earth, flux from the sun at the Earth, and the equilibrium temperature, 255 Kelvin. That's the depressed temperature when you have not included carbon dioxide and other greenhouse gases. You can see its period is 365.24 days. That's the familiar year that we experience here on Earth going around our sun. And if you go down to the second row, you see Proxima Centauri B. We talked briefly about that last time. And it is going around a red star, red dwarf, class M, spectral class M. And the planet going around it is at least 1.3 times the mass of Earth. And it has a radius between 0.8 and 1.4 times that of Earth. And the radiant flux it receives from its parent star is a little more than half of what we receive. So it has a correspondingly lower equilibrium temperature that is averaged over the total surface of that planet, 234 Kelvin. Again, just as was the case with Earth, if there are sufficient quantities of greenhouse gases in its atmosphere, you could expect there to be at least some locations on its surface that have a balmy 50-degree Fahrenheit atmosphere. So keep that in mind. But
Can I
it
ask a
does go
question?
around. Yeah, sure. What's up?
Is there kind of a reason why we're tending to find these exoplanets around M-type stars? Proxima Centauri, but yeah, it has M-type stars. They're having a planet, Ross 128 B is a planet around a red-type star. These are all M3 spectral class. I mean, is there a particular reason why we're finding a higher order of exoplanets around red giants? Is that because of the detection methods, or is that because it's more likely to have planets around a red dwarf star than it is some other types?
Sure. So it's a lot of things. I'll go through them. The first, in no particular order, is that smaller stars are just more plentiful statistically in the galaxy. If you were to make a histogram of all the stars in the galaxy based on their mass on the main sequence, the really heavy ones at one end, the really light ones at the other end, and these M-type stars, the red stars, those are the low mass ones. Those are easy to make in terms of the galaxy just producing stars, and so they're far more plentiful in a relative fraction to the heavy, their big brothers. So there's that. There's that aspect of it, and then, as you mentioned, the selection bias based off of the detection method. They'll produce a stronger signal when the mass of the star is small, so that even a small planet will produce a sizable gravitational tug if you're using the Doppler shift method, and larger planets that are even further away than you would ideally want will still produce a sizable Doppler shift signal on its parent star. So there's a couple different things going on. Those, I think, are the biggest ones.
You said histogram. Was that the original Instagram? Like history and Instagram?
Kyle. Oh, Kyle. That's why you're the best, man. So then we so just I'm not going to read through line by line can you hear me?
Can.
Okay, cool. All right. I got really quiet. That noise went away. That's good. Now I could hear myself think. So I'm not going to go through the entire list, but I'm going to bring your attention to one other one that I find particularly interesting. Okay, if you look at Gliese, second from the bottom, Gliese 667 CC, and the parent star is Gliese 667c. It is again another one of those M-type stars, and it had the planet has a mass almost 4 times or more than the mass of the Earth. So that's a good thing, okay, because it's going to hold on to its atmosphere more easily if it truly is a terrestrial planet with some form of an atmosphere. You'll be much more likely to retain that, and a thicker one too. And it's likely, if you look at its radius, it's at least the physical size of the Earth. It says 1.1 to 1.5, or as high as 2 times the diameter of the Earth. That is a good thing. You don't want something too big, because then the numbers might start becoming ambiguous as to whether or not it's more like a Neptune size and composition object, which is a gas planet, and those aren't good because they don't have a surface, obviously, in which case you'll be forced to look at its moons, and that's a lot harder to do. So if you're talking about a planet that's just a little bit larger than Earth, and a little bit more massive, it's going to have roughly the same average density, so it's going to probably be a terrestrial rocky planet with a nice surface, and it's going to have a lot of geology, a lot of plate tectonics, volcanism. These things are good for for planets. And what I will say is that the larger the planet, we're going to get into this more later on a specific slide, but the longer you will retain a magnetic field that the planet generates. This is important because then you're going to protect the biodome from harmful ionizing radiation from the parent star and cosmic radiation. Why is that the case? Because a larger planet, if you look at the volume of a sphere and you compare it to the surface area of a sphere, the surface area is where heat is lost. The more surface area you have, the more heat you're going to lose because you have more surface area to dissipate that heat radiatively out into space. And so if you recall from high school that the volume of a sphere goes like the cube of the radius, and the surface area only like the square of the radius. And so if you look at the ratio of the volume to surface area for small planets like Mars or Mercury, you're going to have a lot less volume and a lot more surface area comparatively to itself for that heat to be lost. And so you're going to have planets whose interiors freeze, so to speak. They lose all their heat, most of it at least, and they lose their dynamo. The dynamo drives the magnetic field, and the magnetic field shields the biosphere or would-be biosphere from harmful ionizing radiation. You follow me? So that's why Mars.
Can I ask a question?
Sure, please.
And somebody in the live chat actually had these same. I literally was writing down this question, and somebody asked the same thing. But when you're talking about the size differences with the planets, like whether it be 1.5 times the mass of Earth or smaller, that affects obviously gravity in a particular way. How would that mess with number one, how life could grow there organically, or two, if we were to go there as humans as we are now and try to colonize, so to speak, the planet?
Either one of those questions I could talk for an hour about. Oh my god, great questions. I'll try my best to keep it succinct and direct. How would the gravity affect life in some way or another, I guess is what I got from that one. So yeah, you'll notice that if the gravity's considerably stronger than on Earth, even 1.5 or 2 times greater than what it is on Earth, you're going to start to see a change even in vegetation. You're going to need a stronger sort of cell structure. I know trees have that sort of cellulose, what's it called, that allows them to be flexible and grow tall under their immense weight under 1g of gravity. If you double that, you're going to have problems with structural integrity of even like ferns and grass. Things will sort of bow to the gravity a little bit more readily than you might see on Earth. Also, water transport, which is based off of capillary action. In the case of most plants, including trees, there would probably have to be a little bit of a different biological skill set that exploits other principles of physics in order to circumvent the increased gravity. Animals would be affected by it. You would probably see, by and large, shorter animals. Even especially humanoids would probably a little bit shorter than the average human being, the average earthling. Or else you would see some pretty impressive anatomical and physiological tricks in order to pump blood around the body in an efficient way. Hearts would probably be bigger. Bones would be denser and stronger. Walter Lewin has actually an MIT lecture on looking at the ratio of the length of a bone to its diameter and finding any power laws that result naturally. These power laws are oftentimes universal. And so on a planet with more mass, more gravity, you would see a change in the biomolecular structure and physiological characteristics to circumvent these increased forces. Conversely, and kind of more interestingly, if the gravity were a lot less, things could conceivably grow really tall, jump really far, have weaker hearts and less dense bones, more agility, less body mass. It would be like everything would be like a frog in terms of its agility on a planet with a lot less mass. Enough of that. The second question was what again? Can you repeat that to me, please?
How would it affect if we were to go to one of these planets, like from us now, not being organic? We're coming from our gravity that we're used to here. How would we adjust to that sort of gravity? Like, what would they use to anchor us down, or lighten us up? I guess if it's denser.
So there is a way to preemptively solve that problem, and this is something that I had in mind for a future talk. I'll give a little teaser here without further description. If we were to use a spaceship that has a constant acceleration across interstellar space en route to said planet, one could actually live comfortably within the middle-aged years of a human lifetime, even inside a decade, en route to a planet hundreds or even thousands of light years away with a constant acceleration of 1g. And you can get there even faster if your ship's propulsion technology can withstand it, and structural integrity of the ship to do, say, 2g or 1.5 or 1 3/4. Here's the cool thing. If you know in advance relatively accurately what the surface gravity of the planet is that you're going to, you could just accelerate at that rate the entire way there, and so your body will adapt en route. And you'd be surprised how adaptable humans are. Most life, actually, I can't think of any life form that is alive today that's resistive to adaptation.
Flat earthers.
Change. Right.
Yeah, flat earthers.
Right. Absolutely.
They're not really human, though. No.
They're probably physiologically too with them, I would imagine. In any case, humans could conceivably, even inside a year, easily, I'm just throwing out a number, inside a year, and the trip would take, or the ship's frame of reference between, depends on the acceleration and how far you're going, but 10 years. And you could, by the time you get there, everyone would have higher bone density, stronger hearts, more muscle mass too, even just from walking around. And maybe their lungs might even change a little bit they would adapt a little bit and be able to absorb more oxygen. So you could conceivably do it in such a way, if you're smart about it, and sufficiently cautious, so that the crew start out as puny earthlings, and when they arrive at the planet, they're like super strong. Not necessarily like huge muscular, although they would be a little bit strong, considerably stronger. It would all be inside their bones and their heart strength and so forth. And so if the gravity were a lot stronger and you didn't condition them, then you'd have considerable problems upon arrival. Steve?
I got to follow up on that. Well, two questions actually. So when you're talking about like power laws, are you talking to things like I'm familiar with in biology, it's something called Keeler's law, which is basically a ratio of how much the metabolic rate of an animal is comparison to their actual mass, right? Right. So that's like yeah, 3/4 to the power of the mass, right? So there's a ratio. There's a correspondence on Keeler's law. Is that a law that just is because we are animals on this planet, or would that be different on some other planet?
No, actually, Nova has this awesome 45-minute special on fractals. It's one of these intrinsic and very deep-rooted, like fundamental laws of the universe that transcends specific anatomical phenotype and physiology. It's related to how heat is transferred through the body. Yeah, how
there's a heat dissipation factor involved in that, right?
It's kind of similar to this thing I was talking about, where how Mercury and Mars lost their heat quickly. Elephant, in terms of its volume to surface area, again, it's a ton of volume, comparatively small surface area, normalized to a mouse that has this tiny volume, and comparatively a lot of surface area. So whenever it consumes metabolic energy sources, and it's metabolizing it, and its heart is beating really quick, it's gonna dissipate a lot of heat, and it's gonna have to eat again. And it's similar thing with planets, only instead of metabolism, you have just radiative transfer of heat energy.
What law did you say that was, Steve?
Keeler's law.
What do those elves know?
Yeah, damn them. Yeah, damn them elves.
Go ahead, Steve.
And
So you have a second question?
Yeah, the second question. Yeah. Look, I mean, we're all familiar with like the War of the Worlds scenario, right? If you guys haven't seen the movie War of the Worlds, then spoiler alert. They come to our planet. They can adapt because they have no biological defenses for viruses and bacteria. They have no immunity. If we did ever find another planet, what is the likelihood that we would actually be able to even survive there on any other planet if the conditions for which life had arose there is completely different and separate and then how the life arose here?
Yeah, that's a good question. Essentially,
I try.
just to play it on the safe side, I would say that if there's already a flourishing microbiological organisms on that planet, even if they just showed up in cosmological or geological terms, I mean, we're screwed. Unless we have something crazy like nanobots. You put little nanobots in you, they'll take out anything. You just program them the right way.
There you go.
You're good.
Nanobots,
Yeah.
nanobots, immunity defense system. Okay.
Yeah, you're good. You just, I would imagine, or at least hope, that if we're traveling interstellar distances, we have some pretty fancy schmancy medical technologies like that. I can't wait for nanobots. I sure hope they come someday.
I want the die. I am good at foreplay.
But yeah, cool numbers here. That's a good chart, and these are the so-called conservative ones. Like, you know, kind of, sorta, could be likely planets we might want to investigate. TRAPPIST-1, the TRAPPIST-1 system was all the rage. When was that? Pretty recently. It's got 7 planets around it. I mean, 7, not 1. Like, you know, and I think that was, even till this day, the one system with the most planets confirmed to date. That it doesn't mean that some of the systems we've confirmed a planet around doesn't have others that we haven't detected yet, but in terms of confirmed planets, TRAPPIST-1 takes the cake.
It also has the most amount of planets in that relative habitable zone and
Yeah.
Earth-like, right? So that's also like something that's.
It's got like 2 or 3 or something like that in the habitable zone and or on the edge. That's pretty wild. Okay, let's see. What do we got here? Dave, could you iterate us to slide 20?
Don't you so want to go there and check them out, though? I mean, if you couldn't even land or whatever, just to go check them out, that'd be just freaking amazing.
I would love it. By the way, before I talk about this slide, did you guys hear about that? I don't know if it's still a thing, but there's like some Russian billionaire that was thinking of investing his own money into the development of a nano swarm of like little tiny robot, like spaceships that would be propelled to 20% the speed of light using a ground-based
Project
laser.
Starshot.
Yeah, Starshot. And they would just blast it past the Proxima Centauri planet and take a picture.
Yeah, is that based on like a von Neumann principle? Is that like they're going to be like self-replicating as well, or is that just
not this generation,
not this
but it would
one.
form. You got to start.
But future generations would have to be. That'd be the precursor for any kind of von Neumann type of. Okay,
it's a cool idea though. It'd get there in 70 years.
Cool.
So here's the numbers. Check this out. Suppose, just for argument's sake, it takes 10 years from right now for that to come to fruition. We got them. We got the lasers. And by the way, there would be an entire nuclear power plant dedicated just to powering this badass laser. They would have to figure out some ways to get around the atmosphere or mitigate energy dissipation from the atmosphere. Because forget about putting one of those things in space, in orbit. But suppose 10 years, we got the technology, it's paid for, it works perfectly, and we launch them. Traveling at 20% the speed of light to roughly 4 light years away would take 20 years of real Earth time. And then they fly by this planet and we thread that needle, and we're just at the perfect distance to snap like hundreds of pictures. Snap, 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 and they have just enough power left to beam all this data directly back at Earth. And then the light takes not 20 years, but traveling at the speed of light 4.25 years to get back to Earth, and then we get the data, and scientists are like, cool, look what we found. So it's 20 years plus like 4.25, 20, call it 24 years, plus the time it takes from right now to when the technology is produced. I called it 10 years, 34 years minimum. We could have pictures of an actual alien planet around the Proxima Centauri system, where there's a confirmed exoplanet there. And we're trying to figure out, like, how habitable is it? Let's take a picture. Think about that.
Yeah.
The sky would be the most the thing to see with those two the two suns.
Oh yeah, that would be awesome.
Proxima's a 3-star system.
Yeah, 3 stars. It's called. I think
you can only see 2 at a time, though.
Well, one's a real hard. The one that has a planet is as I think is Alpha Proxima B, right? It's a red dwarf star. Yeah.
Yeah.
So it's a slight tangent, but I got to ask. Talking about pictures. When the hell are they going to finally get all the data together and they're processing it? But when are we actually going to get the first actual picture of a black hole? It's supposed to be this year. Do you know when?
Between this year and sometime early to mid next year.
That's so vague.
They're gonna have a direct picture of it's called Project Event Horizon or something like Event.
Yeah,
Horizon.
and they've been toting it for how long now? They got to
well,
get
hey,
that.
man. They're doing
man.
A lot
I've been waiting for that. That's going to be like the greatest thing ever.
You're preaching the choir, man. I sometimes wake up at 3 a.m. and say, "Damn it, where the hell is that picture?"
I've done that, dude. They've done that, dude.
There was a person in our Discord that today was convinced, and he cited the guy's name, but can't remember off the top of my head. Let me find it, and I'll see if you've heard of this guy. But he says that this particular individual disproves or casts enough doubt on the existence of black holes that they're.
Okay.
Hold on. Let me find his name.
Please, we're intrigued. You know, there was an article. Again, there was an article that came out a long time ago, and it was total clickbait. You know, pop science BS. But it was like Stephen Hawking said something about there are no such thing as black holes, and you know, there was one type of black hole that they had theorized, but then they determined that one type can't happen. But the way the pop science put it out there was that black holes don't exist, and it's like nobody said that. This is
quote
stupid.
mining, cherry picking, like.
You remember that?
You know what I mean?
You remember that, Dr.
Yeah, I
Croon?
did.
You know what I mean?
Stephen.
Yeah, it was.
Yeah.
Stephen J.
bogus.
Crothers. Stephen J. Crothers.
Crothers.
Right.
And he was
And
like,
what
"There's
does he
no
suggest?
black holes."
Yeah. What's his reasoning?
I'd have to go to the. Let me click the article real quick. It says that black holes Okay, here's the title of the paper. It says black holes, unicorns, and all that jazz. The notion of a black hole gobbling up matter, twisting space-time into contortions that trap light, stretching the spaghetti-like strands as they move inward. Let me see if I can. Sinister black hole, these claims are unfounded. It's asserted that black holes range in size from micro to macro. I have to go through and read this entire article, but just the fact that he says that there is enough, I guess he's making it sound like there's enough doubt to call it into question. And I was just like, no, I think that's pretty much a concrete, settled thing that black holes exist. Can you? What would be your answer to that? Like, how do we know they are confirmed? Phenomenon that happens in space.
Yeah, so my favorite is going all the way back to the canonical black hole binary system, Cygnus X1. I wrote a paper on that, and it was an X-ray source and the constellation Cygnus, hence the name Cygnus X1, that we were gathering data on as far back as the 60s. And obviously, through the decades, our data got better, our instruments got better, and we constrained the physical size of the X-ray source, and it was like almost like a point-like source until, at most, until Chandra came along. Chandra is an X-ray telescope, a space-based telescope. It has an extraordinarily high angular resolution. You can resolve like angles, and I apologize, I don't have the number, but suffice it to say, it's a badass telescope. And we were like, okay, so we have this bright X-ray source here. There's a star, right? There's this, so that's what a binary system is. You have the candidate black hole here, and you have a star. It's a big like O star, and they're orbiting around each other over a period of so many years. I don't remember that number off the top of my head. And when you look at it in the X-rays, that star disappears because it's not emitting much in the X-rays. It's mostly in the ultraviolet and optical. It's a bright O star, and you see this other source over here, not where the star was before you blinked it out, and it wasn't there before. And when you look at it in the optical, and you can constrain the physical size of that, and you can calculate the total luminosity, how much X-ray energy is being thrown off. And when you run the maths, and it's really simple back the envelope stuff on its like how concentrated that energy is. You can use the Eddington formula, for example, which calculates the luminosity of an object that's accreting matter. So you have matter falling onto a dense object like a neutron star, which this was not, because we would have seen that already. It was just completely invisible until you look at it only in the X-rays. Anyway, Eddington's formula says if you have all this matter falling on it, you're going to have some amount of energy in the form of light rays, like electromagnetic, X-rays, gamma rays, UV, whatever. And we use that to infer the number of solar masses of like denseness that was right there in the middle, and a really tiny size producing X-rays. You do the math, guess what? It's the Schwarzschild radius type object. It has a mass of about 10 to 15 solar masses, and so many kilometers of diameter and size based on a Schwarzschild radius that we would that we already know of for a non-rotating black hole. Or you could use a Kerr black hole formula. Anyway, so the numbers check out. You have, I mean, if it barks like a dog and it looks like a dog, it's a dog.
Here's what he
Sorry,
claims.
get over it. Yeah.
I found a summary of his claims just really briefly. He says that there's been a deliberate suppression of scientific truth by the community of physics and astronomers concerning the black hole and Big Bang. There is no theoretical basis whatsoever for the existence of black holes. Neither Newton's theory nor Einstein's theory predict black holes. Both theories preclude it. Black holes are the result of David Hilbert's corruption of the so-called Schwarzschild solution. Schwarzschild coordinate singularity at r equals 2m is non-removable. The singularity theorems are not theorems at all, as they are based upon false concepts. It is possible to have M3 and E3 in one-to-one correspondence. Einstein's gravitational waves are fictitious. Einstein's pseudo tensor is meaningless concoction. The universe is not expanding. The cosmic background, the cosmic microwave background is not cosmic in origin. It's produced by the oceans, and the Big Bang is creationist claptrap. The Big Bang is creationist claptrap. That's the last you take away from this.
Wait, I got a question. How much fractal wrongness can you get into one freaking statement?
That was impressive.
I don't know.
There.
I don't think I could do that. I couldn't do that if I. Well, I could probably if I tried really hard. But I wouldn't want to.
Yeah, can you link this to me? I'm not going to look it up.
He's a crackpot. He's a crackpot.
Wait
a minute.
Just,
Listen,
I mean, they're complete lies.
Hold on. I can't believe that the individual that was arguing this in the Discord is using this gentleman. Let me read to you what his the first line on his about me thing is on Wikipedia. Okay, Stephen J. Crothers was born in 1957. He is a handyman and gardener and a part-time amateur scientist who claims that black holes do not exist. Sit down, please. I think I have more experience with science than
Who is it in the live chat?
and that's not a
Are they
lot.
still with us? Wait, are they still with us in the live chat?
No, it's not.
Is that?
It's on the Discord.
It's on the Discord. Okay.
Yeah.
Yeah. Not gonna get into the details about half the stuff that he was talking about, but there might be some issues with singularity. I'll concede that point, and maybe Dr. Croon can touch on that if he wants to. But the rest of it,
he's a handyman. Why even entertain it? Dr. Croon, please pick up.
So, can I say something? Like, what the hell?
Sure. But real quick, Dr. Croon, I mean, simply put, if we have a hypothesis where we can say, look, if black holes exist because of the math and the physics, if we expect to see a certain mass of an object with a certain amount of accretion disk, with having a certain amount of X-rays at a certain energy level, and we find exactly those parameters and X-rays at those energies levels, that would be a very good confirmation of our prediction that there's a black hole there based upon the mathematics and physics. Would you agree?
Yeah, absolutely. I would say one of my favorite mottos is there can be no stronger test of an idea than its predictive powers. If you say, I predict this, exactly that, here's the exact number to 3 decimal points, and here's this, this, and that because of this, and I give you a nice, neatly wrapped a hypothesis with a prediction, and you go and do the observations that have never before been done, so there's no way you could be like fabricating your prediction, and it matches. I mean, that's a powerful test of the idea, and that's exactly what we've done over and over and over. And what Kyle read was just a mindless rambling of completely false, fabricated lies that are demonstrably false and known by any sane, rational person to be false. And he gives zero evidence, even for a single piece of his mindless rambling on and on and on, for stuff that we have established as fact. Fact is fact. Get over it. It's true whether you believe
Facts
it or not.
don't care about your fifis, people, okay?
Oh, let's bring back a word that Dr. Croon used in the last appearance that he used with us, because this is well deserving of that, and that would be a booyah.
Oh, yeah, I remember saying that.
Booyah!
And then I eventually moved to boom, to boom, to boom.
We need to have an episode with your Discord friend, because I don't know who this person is, and maybe get him on to see why he thinks that rambling was coherent.
He was going toe to toe with it, that's for sure. Okay, sorry, Dr. Croon, I didn't mean to pull you off of course here.
No, it's fantastic. It's fantastic. I'm just trying to gather my thoughts and try to figure out that. So what I'm trying to do here, so we have this table here that's been up for like the past 10 minutes, and people have probably already perused through it. But what I would like to do, kind of like with the previous one, is to pick out some notable features. I'd like to impart upon my audience tonight, as well as you, good sir and sir, some interesting things to look for whenever you in the future have a article pop up and you click it, and it's talking about some new exoplanet that's been confirmed. They're coming in all the time. I remember from the previous show I said that on average 2 to 3 exoplanets are discovered every day. 2 to 3 a day. And you probably hear about the most amazing one like in every 6 months or so. I don't even know. I peruse the annals of scientific pop culture and little news articles for the average person, and I don't see them every day, and that's because they're only showing you like the big ones, even if they're not confirmed. There's that one about the diamond planet, and I even looked up after last show and found that maybe they think it might not actually be diamond planet, but it's definitely carbon rich and blah blah blah. So there are some clickbaits out there, but what I want you guys to know and sort of start to appreciate are some of the key numbers that might be the most pertinent for your initial considerations of a newly announced exoplanet. Steve had so astutely observed earlier that so many on this small list are M-type planets. These are that first letter there, capital M, tells you that it is very small. So red dwarf star. There's, as I said before, there's just so many of the small, the G, K, and M stars. More so with the K and the M stars than like the O, B, and the A's and the F stars. The little small red dwarfs are just so plentiful. They're just easier for the laws of physics to conspire upon a faded cloud of dust and gas and to generate these little guys. The other thing you got to keep in mind is that the smaller the initial mass of the star, all things being equal, the metallicity has a small contribution here, but the smaller the mass of the star, the longer it lives. I mean, some of these suckers, little red dwarfs, can live 100 billion years on the main sequence, or more, tens of billions to hundreds of billions of years on the main sequence. Our sun, more massive than these little red dwarfs, it'll be about 10 billion years on what's called the main sequence, where it's just young, healthy star fusing hydrogen in its core, hydrogen, deuterium and all that. And then it does all this other crazy stuff, becomes a red giant and all that, which it lasts only millions or tens of millions of years on the giant branch. These little guys last so long, and by the same token, the really massive like O and B stars, they sort of like live bright, die young sort of thing. They live like the O stars, the most massive ones, live a few million years to a few tens of millions of years, which is nothing on the cosmic time scale. And they'll go supernova, whereas the little red dwarfs won't ever go supernova. They'll just sort of putter out hundreds of billions of years in the future. And the universe itself is only 13.87 billion years of age right now. So I bring your attention, without further ado, I throw in these little astrophysics tangents sometimes. I love it, obviously. If you look over here at the top, what's a good one? Okay, Ross 128b. Ross 128b. It's an M4 5-star. That little V, it's actually a Roman numeral 5, which means it's on the main sequence. Surprise, surprise. M-type star, still on the main sequence. No surprise there. Mass of the planet is at least 1.5 times that of Earth. Radius 1.1 times. 1.38 times the solar flux on the surface of the planet than Earth does, which is surprising because it's a red dwarf, which means it's going to be really close to its parent star. And lo and behold, what do we see here in the period column and units of days? 9.8658 plus or minus 0.007. If my students are listening, what did I tell you last week? If you write a number down and you have that many digits after the decimal point, that means you know them. And you add in your uncertainty. A number means nothing without its uncertainty. And here we see that they know the period of this planet is 9.8658 plus or minus 0.007. Booyah!
You don't beat your children. You don't beat your students, dude.
I take it you were teaching them about significant digits. Is that?
We were, yeah, like all month now and again.
Okay. By the way, students, significant digits. Understand them. Trust me, because there's a reason why we use significant digits. Okay.
Or Steve will bitch at you on Twitter forever.
Exactly. I will find you. I have my ways. You don't want me to get started on Twitter.
He will find you, and he will tweet you. I don't know who you are, but I will find you, and I will tweet you.
You have no idea what I'm capable of.
That was a good booyah. I was building up to that one too. All right.
Poor student.
All right. What do we see here in the equilibrium?
Scared.
In the equilibrium temperature in kelvins, so we have 280 Kelvin. That's like I said before. You got to remember these could be artificially deflated average values because you have not included a greenhouse gas effect. So that's fine. 280 Kelvin, by the way, that is. So let's see, 273 is 0 Celsius. So 280 is 7 Celsius on average. That's like like 22 Fahrenheit.
Teacher, you have a student here.
Yeah, I don't mean to interrupt, but you actually have some students watching in the live chat, and they just said to let you know that they are watching. You have a Rod. That sound
A
familiar?
what?
Roman
What?
Ahmad.
Roman. Yeah, Roman.
Yeah, Roman.
All right. Nice. Anyone else?
If you're watching the stream, let us know in the live chat so we can say hello to Dr. Croon for you. And if you need us to like call services for you, we will.
And because Kyle had brought this up earlier, and maybe I think we can kind of touch on it. He wanted to know what kind of apparatus discovers the planet, and so like Ross 128b. Do you know which it was? It was HARP, by the way, that discovered that. But can you tell us a little bit about that particular telescope or planet searcher? Do you know anything about HARP?
Oh,
HARPs.
I don't
It's
know.
called HARPs.
I don't know that one. Harps, really?
Yeah, high accuracy radio planet.
Oh, right.
High accuracy radio velocity planet searcher. HARPs.
I thought it was TESS or something like that.
It's TESS too.
TESS
Yeah,
or
TESS
something like that.
Herps.
Yeah. There's also TESS.
But yeah, TESS.
TESS is the transient exoplanet. Okay, I'm gonna get this right. Transiting exoplanet surveying satellite. TESS.
Yeah.
Right?
Mm-hmm.
Yeah. So there's TESS and there's HARPs.
Right. Okay. So yeah. That makes a lot of sense because these are ground-based spectrographs that use the Doppler shift method. So I was talking about the planet that whenever you have a red dwarf star, that's the parent star, its mass is the smallest of any of the whole spectrum of star masses. Red dwarfs are the lightest one, hence the name red dwarf, right? And so it's much more susceptible to gravitational wobbles from any of its planets that are orbiting it. And there's two things that make the wobble more extreme of that star. Having a planet close to it, like having an orbit really close to the parent star and going around really fast, or having a massive planet. If it has a lot of mass anywhere, at any distance, it'll have more of a tug than a smaller planet at that same radius from the star. So HARPS, yeah, it's ESO's 3.6 meter telescope at La Silla Observatory in Chile, and it's discovered over 130 exoplanets to date, with the first one in 2004, making it the most successful planet finder behind the Kepler Space Observatory, which we talked about almost exclusively last time. And so you guys remember the Doppler shift? So you just have this sort of tug of war gravitationally between the small planet and the comparatively more massive parent star. And we just saw that if the parent star is low mass, it's more susceptible to larger wobbles. That'll give you a larger signal for the spectrographs to actually detect a planet gravitationally, I guess, tormenting the parent star in a sense. So that was there any other question I didn't answer?
So far, just so that you know, so far I count, going back through, I count about 7 or 8 that are at least letting us know that they're watching.
Cool. Okay. Nice.
So welcome, Hawks. Thanks for joining us.
Okay. Where was I? Right. What was I saying? I got off on that booyah thing with the.
That's okay.
The
You would like that booyah moment.
Yeah,
we were talking about Ross, I believe.
Right, Ross 128b, and since its designation doesn't start with K, so that's not a Kepler planet. You said that was a HARPS planet.
That was HARPS,
a planet detected by HARPS. Okay, cool. That makes sense. Now, but and that makes sense about the sig figs, the digits and the period of the actual year of this planet around its parent star, 9 point blah blah blah. Those digits of accuracy are due in no small part to the resolution of that spectrograph they have at La Silla Observatory in Chile. which is, of course, high up in the mountains, so they're above most of the water vapor, which, of course, mitigates atmospheric effects on that light and helps them get accurate results like this. This system is a mere 11 light years away. That's not that bad. It's 3 times farther than the Proxima Centauri system, right? That's just, in fact, all of them on here are no more than, I guess, 21.35 light years away. That's like right next door. That is not far. Remember, the galaxy's 100,000 some odd light years in diameter, at least. So 20 light years is nothing. But here's the thing. I saved this for the end of the discussion of this particular slide. Do you guys see something that's good and something that's really bad about this planet? There's one of each, and I will tell you what those things are. The good thing is that the equilibrium temperature is 280 Kelvin. So over the whole surface of the planet, that's its average global temperature. And that's good because that means the average temperature, even without the warming effects of any atmospheric greenhouse gases, CO2 and methane, for example, its average temperature is above the freezing point of water. So you could...
That's about 44 degrees for us Americans, by the way. For people that don't do conversions, 44 degrees is what that comes to. So for us American people, screw the Europeans that use Celsius. We don't do the metric system here. We should, though.
Steve, are you sure about that number, though?
280 Kelvin?
280 is, so 273 is 0 Celsius, so 7 Celsius is 280.
Let me check here. 280 Kelvin? 280 Kelvin to Fahrenheit, right?
So wait, 0 Celsius is 32
280 Kelvin
Fahrenheit. Right, so 40, you said 44 Fahrenheit.
Yeah.
Okay. I heard you wrong. Yeah. Thank you. Makes sense. Sorry. And it's
Kelvin
probably
is based on
more
absolute
than
zero, that's all, right?
Yeah. Mm-hmm. Yeah. So Kelvin here, it could be warmer, just like in the example I showed you with the Earth, how once you add in the greenhouse gases, you get a slightly warm. I mean, that's what greenhouse gases do, and these are good for a biosphere that wants places like warm tropical beaches and year-round fisheries that are nice and warm, and you can go on the beach and there's fish everywhere and stuff like that. A booming biosphere. So that's good. But what's the bad thing on here? Not the temperature. Go back to that period. 9.8, whatever, just say 9.8 days is its year. So remember,
it's really close to this planet.
Kepler's laws will, once you plug in the mass of the planet, the star, you don't need the mass of the planet, the mass of the star and its rotation period, you get the square cube law thing. And so that means it is really close. And especially since the gravity of that star is low, it's going to be really, really close. Like it's going to be skimming the surface. And
that's going to need a high degree of electromagnetic radiation and ionizing radiation bombardment, right?
Yeah, and the thing about red dwarfs is they are temperamental. They have these loud periods they go through sporadically, where they are having these flares. Some flares could be a low-level extinction event. So you could have a near sterilizing level flare where you have just so much ionizing radiation that just gets blasted off the star's surface that it will overwhelm the planet's defenses. There's 2 defenses. 3 if you count the implicit defense of its distance, which in this case doesn't count for nothing since it's so close. But the other 2 defenses are its magnetic field and its if it has any ozone, which would absorb mainly photons, which have, they're not made of matter. They're just like light, like ultraviolet or X-rays, which can be, of course, extremely harmful to biological entities. And they don't give a crap about the magnetic field. It goes straight through that. They hit the upper atmosphere and mid-level atmosphere layers where you have a lot of ozone. O3 will photodisassociate, thereby absorbing those ionizing photons and prevent them from reaching the surface. Some of them still do on a daily basis, but it's a mitigation, and that's the same sort of thing we have going on here on Earth. Except for the ozone hole above the South Pole that Landon was telling us about. But during a flare, the ozone isn't going to do much. You're going to have just too high of a energy flux of these harmful rays, ultraviolet and some soft X-rays reaching the surface, and any biological life forms, even bacteria, are going to be extremely damaged. They're going to be killed or get cancer and die later, just in time for the next flare. And so you would expect there to be not a whole lot of a chance for life on the surface of a planet like Ross 128b, or on its moon. Like if there's, like I was saying, if there's some moon, maybe go there. But it's the same problem. It's too close. The problem with the magnetic field when it comes to plasma, like charged particles, like actual plasma, radiation, electrons and positrons coming at the planet, the magnetic field will take care of some or most of those. But here's the thing again: when you're that close to the star, you're in what's called synchronous rotation. You're tidally locked, sort of like the moon is around Earth. So you always show the same face. So its day equals its year. Think about that. So it goes around its parent star in the same time that it rotates on its axis. And so what that means is that the dynamo is generated from the core's rotation, the inner core's rotation. And now I understand that the rotation of the planet, because it's a differential rotation, doesn't one-to-one correspond with the core's rotation rate. But let's just say that it is. That's going to create a weak magnetic field, because the higher the spin rate of the core, the stronger the magnetic field. And you want a strong magnetic field to protect against these plasma particles. And since it's so close to the star, it's going to be tidally locked for sure. So its day is going to be equal to its year, which means its core is going to probably be rotating kind of slowly, which in turn means its magnetic field is going to be. So look at all the physics there. Don't you love that? I just looked at the length of its year and told you that life will probably be sterilized on the surface. That's cool. That's why I love physics. That's why I love physics.
Booyah.
Booyah.
If only it were real and not some
here's
CGI magic by NASA. If only it were real.
Yeah, is this planet? Yeah, because how do we know this planet is not procedurally generated? It may not even exist until we go check it out, right?
Yeah, it's paper. It's just a light in the sky, right?
Yeah, that's it. Not less processing power, just light, right?
It's just a bunch of pictures put together to make one big Earth. They fail to realize that it's a composite of a real pictures of Earth. Like what it's made of are the real images of Earth.
They just seem to skip that entire part. I don't know.
So I figured out how to make a flat earther disappear. Take a picture of them and then just change the light level slightly in Photoshop, and now it's CGI. They're fake. They don't exist.
That's hilarious. I love that.
But hey guys, so I've just given you a lot of doom and gloom about this poor Ross 128b, but I believe that this show is not about kicking candidate planets that have been confirmed planets off of the menu for possible life hosting planets. And so here's what I propose. It's all about using in a clever fashion the laws of physics and the principles of nature in order to imagine how life might get around these harsh conditions that I've just demonstrated would be all but overwhelmingly destructive to any life forms that are on the surface. Notice how I said that I was alley-ooping myself because I was anticipating this aspect of the conversation, whereby I say, what if life were to develop and flourish under the surface? Why not? The penetration
totally
depth
possible.
of ionizing radiation and the form that it would be near a red dwarf, it's not going to penetrate more than a few meters, especially if you're talking about solid rock. Ultraviolet rays are stopped just by your skin. X-rays a little further, a meter or two. And if you're talking about more softer things like soil, okay, it'll go a little further. We're talking about meters here, guys. You could have, subsurface aquifer. I mean, aquifers like on Earth are all over the place under the water table. You can have subsurface, like essentially like lakes that are completely shielded by all the whims of this red dwarf. and could potentially host single cell, even multicellular life. You could have Ross 128b catfish that glow purple and are 20 feet long, and jellyfish the
It's
size of a
Atlantis.
laptop. It's Atlantis, only it's 11 light years away, and I would love to visit there. So
Isn't
think
that
about
isn't that
that.
what they think about Europa as well?
Yeah.
That they're
Mhm.
they're wanting to drop that submarine. I think they're talking about doing now, but that's what they believe that's going on in Europa.
Yeah, so Europa could conceivably have more liquid water, like water, than all of the water on Earth. Stand at the Pacific Ocean shore and look at this vast ocean, and then say to yourself, I was watching this NonSequitur show with Dr. John Croon. He said there's more water over there on some moon than all of this. Oh, come on! But it's mind blowing because it's quite possibly true, because you're gonna have an ice crust, and then like hundreds of kilometers thick of water that gets higher and higher pressures as you go down, but it could remain more or less regular liquid water for hundreds of kilometers. The deepest part on Earth is not hundreds of kilometers. Even the Mariana Trench is what, like 10 kilometers, like 7 miles or something like that.
That's so
So when
creepy to
you
think
I think
about.
it's a little deeper than that. But why don't we do the Starship project to like Europa? Why don't we send a bunch of nanospots over there at light speed and have them go check for, I don't know, whatever kind of metabolized gases or carbon things that we'd expect from organic life of some kind. Well, I mean, and a good way to test the theory too. I mean, how long would it take to get to Europa if we're going to be accelerating them up to like 20% of the speed of light or something?
Oh, you
They
get
can't
there
break
in
through the
like
crust
three.
though.
Yeah, they can. They
Well,
have
I mean,
this
yeah.
drill that like melts it. You have like this like heat that you apply, and it just sort of melts its way through.
So why don't they
It's
send
one of the
nanobots to
systems.
another planet, or in this case a
Yeah.
moon? But why wouldn't they do that? Why are we waiting to send it to
Eventually,
Alpha
yeah.
Centauri or Proxima Centauri when we have a potential moon right here that kind of life, and then we can get there in a matter of what, days? I don't know, weeks, months. I mean, how long would it take
If you
at 20%
use one of
speed of
those
light?
ion, well, you wouldn't get near 20%. It's just so
Yes,
close.
yeah, it
You'd
wouldn't be
blow
long enough
right
to
past.
accelerate it.
So you could
But it still wouldn't take
easily.
very long,
No, you get there
right?
in weeks with one of
Yeah,
those
the Parker
ion
probe is going to be in
drives.
the sun in a couple months, right? And that's 93 million miles. So
Yeah, you
that's
Isn't
could
still
it
going
easily
anywhere
get
probable?
deeper.
there.
Isn't it probable too that Titan may also have life that's just evolved in that that methane environment, because it has literal lakes that are running with that
Yeah,
liquid methane. So it's
yeah.
theoretically conceivable that life could possibly grow to adapt to those kind of conditions, right?
I'll tell you why I personally think that it's not. And you're right. You're absolutely right. There are entire lakes and seas that we have pictures of from radar where we see lakes disappearing as the seasons go into the warmer, relatively speaking, the warmer months of its year around Saturn, as Saturn goes around the sun, and they evaporate and then they condense over here. And there's even methane rain that, like, big drops of rain like this big that float down through the super dense atmosphere. It's very, very dense atmosphere, almost entirely methane. And so it's a very similar in terms of like erosion. Like, there's erosion of rocks and pebbles and riverbeds that look like something from Earth, only instead of a hydrological cycle that we have on Earth, there's a methanological cycle on Titan. You're absolutely right about that. In fact, we landed a probe on the surface, and
Cassini.
it just right, because it took just a picture, and it was about 2 feet off the ground, and you could look up the image of it, and you see these pebbles, and it's like sort of a grayish brown like atmosphere and surrounding. And if you do some color correction, you could mistake that from a babbling creek bed near somewhere in on Earth in Montana or something.
Absolutely.
And so it's a very similar geological and morphological phenomena there. However, here's why I don't think there would be life there, is because you need an oxidizer for a chemistry tool set for for cellular respiration for it. And so you need the only oxidizer that we know of is oxygen. That's where we get that term. There's very little oxygen, if any. In fact, someone told me, because methane's highly flammable, it's natural gas. They're like, if you were to even have one spark on that planet, then it would blow up in this huge fireball that we see from Earth, right? And I was like, well, like, flammable stuff doesn't just burn by itself. It can't burn. It needs the oxygen there.
Could there possibly be any kind of I mean, you're talking about oxides. Could there possibly be something like perchlorates, which is a big problem on Mars? One of the biggest issues, I think, if we ever go to Mars, is because you have perchlorates there, which are highly oxidative, and so anything we haven't set up there is going to be susceptible to that. Do you think Titan could have perchlorates as well? That would be an oxidizer.
Yeah, I don't see why. Yeah, sure. I hadn't considered that.
It's possible.
Yeah, it's possible. So that doesn't rule out the possibility of some life form. That was just my 2 cents, but good point about the perchlorates, Steve. And Kyle, there you have it. Look for perchlorate combusting bacteria on Titan.
We started a new hypothesis. Perchlorate combustible bacteria on Titan. There you go.
Yeah, and it would be interesting to see what state that compound is in at the temperatures and pressures on the surface of Titan. If it's a gaseous form, or a liquid form, or aqueous or whatnot. So definitely food for thought. Yeah.
Since they one last question. Since they, they're almost positive, I believe, that Mars has now, or either did have, a large abundance of water at one time. So, do you think that at some point that there was life there on Mars, and that we will find it once we, either dig deep enough, or there'll be some kind of bacteria there, or and if so, do you subscribe to the transpermia theory that life from Mars came down here?
Yeah, so it is a pretty well-known fact, especially if you watched the first season of the latest Cosmos with Neil deGrasse Tyson, that when there are asteroid or comet impacts on pretty much any terrestrial planet, you're going to have some, albeit small fraction of matter ejected back out into space, and there could be microorganisms that were preserved inside that rock and survived the heat and the shock waves that blasted through it, and would just sort of trapeze throughout the solar system for millions of years or so, until just by chance coming back and falling back onto the same planet that they were from, or a different one. So you could conceivably have an asteroid slam into Mars and the distant past, when it was a world with water oceans, which the evidence is pretty convincing. If you look at the surface features of Mars, you see bedrock and river flows, and what do you call it, Volusia, what's it called? Anyway, you see a lot of evidence for liquid water flow that have been preserved. Alluviate flows, yeah, those sort of like at deltas and stuff. When you could, yeah, thank you.
My geologist friend is going to like me for that one. Pull that one out of
and
my
I should have remembered it, but yeah. So there's a lot of evidence that suggests that Mars used to have oceans, or some lakes, at least, and rivers, and a hydrological cycle complete with the rain, the whole shebang, guys, right? And so the question is just then, after how many years from when Mars cooled and was no longer like a ball of lava, and liquid water was there as a stable water terrestrial planet, how long after that did life appear? If it did in fact evolve in the same way and independently of Earth, forget about transpermia for a moment, or panspermia, and you'll see that the oldest rocks on Earth have fossils in them. Like, so pretty much as soon as you see liquid water, you have fossils of some microorganisms and whatnot in them. And so it begs the question, if there is evidence that Mars used to have water, then did it produce life as quickly as Earth did? And then a follow-up question, what's the time frame between that point in time and when it started things started running amok on its surface, and it lost its oceans to space, which we'll talk about in a moment how that happened. So I in terms of like the astrophysics, it's kind of cool to see like this impact theory, and then life is carried around, and then it goes from Mars to Earth eons later. But for some reason, I don't like it, because I'm more interested in like the roots cause, like how molecules arrange in such a way as to produce the first life forms. RNA and some prokaryotic cellular life or some sort. And so I just feel like this other idea is a little bit like shifting the focus to just a different planet, and it's interesting, but I don't put it on the same playing field as finding out the answer to how life got started. And that's all I got for that.
Cool.
That's just me. So I would like to go now to, okay, we're doing kind of good on time there. Okay, could we go to slide 24, please? There's a lot of text on here. Don't get too bogged down with like reading this verbatim. I would like to bring your attention to a water world planet, Kepler 22b, and the famous Kepler catalog. It's located 638 light years away in the constellation of Cygnus. Still, it's not that far away. 638 light years. It was discovered in December 2011. Equilibrium temperature of -11 Celsius. Without the contributions from CO2. And as a parenthetical, Earth's equilibrium temperature would be -18 C, which is like -0.5 of Fahrenheit, without the CO2 contributions. So Kepler 22b is dubbed by scientists a water world. It might be an ocean-like planet. If you guys remember that old Kevin Costner movie, Waterworld, think that there might be some smattering of islands and whatnots for you to set up shop on some tropical beach with some exotic fruit. Let's see here. It is in the habitable zone, and an Earth-like composition is ruled out to at least 1 sigma uncertainty, which means that they're thinking it's it's more of like a volatile-rich composition. So volatiles are things that readily evaporate, like methane and CO2 and stuff like that. And things like rock are not volatiles because those don't readily evaporate at standard temperatures and pressures. It's most likely an ocean planet with a small rocky core. It's not beyond the realm of possibility that life could exist in such an ocean. Right there, Kepler 22b, one for the books. Waterworld, Kepler 22b. Remember those terms if you can. What next? So can we go to the next slide, slide 25, please? Okay, so this one is Kepler 61b. It's a super Earth, which means it's considerably larger and more massive than Earth, but not large and gaseous like Neptune. So it's not a Neptunian. It's a super Earth about 1,100 light years away from Earth, discovered in 2013. So that's considerably far. You could get to that in a human lifetime, inside a decade, with proper accelerations. Super Earths are bigger than Earth. Here we go, smaller than ice giants like Neptune and Uranus. So radius about 2.2 times that of Earth, and about 6.65 times the mass of Earth. So it's got a decent mass to it. It orbits its host star with about 8% of the sun's luminosity. So it's probably one of those K or M stars. An orbital period of about 60 days. And so it might be far enough away to not be tidally locked, or maybe not tidally locked yet. Those things take some time. And an orbital radius about 0.28 times that of Earth. Compared to that with Mercury around our sun, it's about 0.38. So yeah, 0.28 is kind of close. It might be in a tidally locked state. It has an eccentricity of 0.25, which means it's kind of kind of mildly elliptical. So the way it works is for a circle. So if you take an ellipse and squash it down to a circle, it has an eccentricity of 0. And as that number approaches 1, it gets more and more squashed and elongated, more oval-like, which is interesting because think of this. Suppose the ellipsoidal orbit were sufficiently elongated so that way the habitable zone, which remember is a circular ring, so you have some inner radius and outer radius that is concentrically and circularly centered about the apparent star. So what if the orbit crosses into the hotter region, like outside of the habitable zone, too close to the star, and comes back out, goes through the habitable zone, and then swings out to the cooler reaches of space outside of the habitable zone, and then goes through it. So it's like just right, and then too hot, and then just right, and too cold, and then just right, and then keeps doing that every time it orbits, which is every 60 days. So it could be an interesting scenario to ponder what the laws of physics would conspire against in order to see what sort of possibilities of life or what challenges that would pose for life. So that's an interesting one. That's why I put that on there, Kepler 61b. And so, okay, I don't need any of that. It's extra information about that.
While you're at a pausing spot, Dr. Croon, we've just let you know we've got about 10 minutes before we get to questions from the audience. If you whether you wanted to like stop now and go straight to questions before you get any deeper, or and just table the rest for the next show, or however you want to do it. But we want to leave room for that. Those audience questions too.
Thank you for the time chat. I have 2 slides I'll just briefly mention. Dave, can you go to slide 30, please? 30. So
what did I tell you when we first talked? Our first conversation. You will never get through.
You did
everything that you planned to with Kyle and Steve here.
Nope, never will happen. Don't even expect it.
If it does, it'll be like we'll have to have a party or something. I don't know.
This means you have to come back though. That's a good thing.
Yeah, absolutely. So this green ring is what I was talking about. That is the habitable zone range, and with the star at the center. And then you could have this is for a different planet. This is Gliese 832c, orbiting an M-type star. And you see with a different eccentricity, it's not as extreme as the one I was talking about before. You see that it swings into the habitable zone on the right. That's the blue curve, but dipping into the green shaded area. And then it could come back and come just inside the habitable zone and receive a tad too much heat and maybe be a tad warm. And so it could be interesting to have some simulations calculate what the sort of average temperatures would be, what the seasons would be like, and how extreme and how quickly these extremes phase in and out. So that way life may have an ability to adapt to that. If they're not super fast, it's a little more balmy transition, you might expect life having the capability of adapting to that. And then if we could go to slide 33, let's look at this little chart that shows some sort of categories here. We have, so this is old, this is 3,700 confirmed planets. I think the latest one is it's more than that, it's like 6 or something. And if you look, so we have giants, we have a picture of Jupiter here. The number 1,217 shows that we have, of those 3,700, about 1,200 are like Jupiters. So you wouldn't look for life on that planet, but hey, it could have a couple dozen moons. It could have like a Europa-like planets around it. You have the Neptunian ones, similar situation. And then super Terrans, they're like larger than Earth, but less massive and smaller than Neptunians. And they do conceivably have a rocky surface with some oceans probably. That's in the case of Kepler 22b with the water world. That was the one I was talking about. The super Terran 982, almost 1,000 there. And then Terrans like regular Earths 700, sub-Terrans like the size of Mars 72, and Mercury-sized mini Terrans about 5. So that's sort of the breakdown for this data set. as something to think about. And
So if you
in
looked at the
terms
Drake
of
equation and you got a fraction of the ones of the Terran planets, just alone using a low boundary conditions for the Drake equation, out of those 701, what would you expect would have life, or would you have for your expectation?
any form of life, I would say I'm pretty optimistic. I would say 40%. Yeah.
Wow, that's actually pretty damn high, and that's
Except
based
for
upon the
if
Drake equation.
no, well, so that's a simulation, right? That you have to choose what values, and
Right,
you could have
right. I mean, let's say you
lower
use
and upper.
conservative values. Let's say you took your most conservative values, and even with conservative values, the lower bound is pretty significant for the amount of civilizations that should exist, right? Could you apply that to say, okay, then out of that, so many planets, then there are Terran-like would have life? Because I mean, 40% seems awfully high. That you're saying that out of 701, that nearly half of them you expect to have life.
So yeah, that would be my upper bound though, and so
Wow. Yeah, that'd be the upper bound, I
especially
think. Yeah.
yeah, and so especially it would be lower, especially if you look at what fraction of those are actually around these pesky red dwarfs, where you have the planet really close and it's plagued with these flares. So that would drop that number down a lot, I think. But if you're around a G star, then yeah, you could have a decent
Ours is what,
number
a
of these planets.
G2V? Is that the sun? A
G2V.
G2V star?
Yeah.
Yes.
Good job, Steve.
Steve done good. Steve get extra credit. Yeah, Steve remembers his astronomy from college. Okay, great.
So I have to I can't call this a completed show in my mind unless I just say a quick thing about the Kardashev scale. It was supposed to be exoplanets and Kardashev scale. I'm just going to mention it real quick, 2 minutes, and then we'll go to questions. And I don't have any more slides.
Yeah, we got to get to that.
Kardashev scale is super quick because in the 60s, this Russian physicist came up with a hypothetical classification scheme for technologically advanced civilizations based on an increase in the size of naturally occurring bodies such as planets and then stars and then galaxies. So type 1 is Roman numeral 1, Roman numeral 2, and 3. Roman numeral 1 is planetary class. They build cities on the ocean. They could stop hurricanes and earthquakes and volcanoes. They've mastered their planet. They're complete stewards of the planet. They utilize all the energy that falls on their planet from the parent star and have mastered the technology such as nuclear fusion. Type 2 is 10 billion times more powerful and are stewards of the entire solar system, colonizing multiple planets and moons in that solar system. And that's the one where you have the Dyson sphere, where they have a huge solar panel in a sphere shape, sort of capturing all the power that their star produces. And then type 3, which is is 10 billion times more powerful than type 2, which is a galactic class, which has they've colonized multiple thousands or even millions of star systems in the galaxy. They use antimatter probably as also the supermassive black hole at the center of their galaxy for exotic forms of energy consumption to fuel their vast civilization, and they have technological capabilities such as warp drive, and so it stops there. 1, 2, 3. And then Carl Sagan interpolated it, made it a smooth progression, so you can have anything from 0 to 3, any number in between there. And Earth, as of 2012, was a type 0.73. And so he estimates, Michio Kaku estimates between 100 and 200 years from now, we should achieve type 1 and be full stewards of our planet and no longer rely on fossil fuels and have all these fancy energy sources of the future, of tomorrow's world. Okay, that's it. That's the Kardashev scale.
I've heard different things. I've heard on the Kardashev scale that Earth is 0.735, but also heard it's 0. Why do you? Is there?
Yeah, because right. So because in the discretized version, it's sort of like Boolean logic. If it's not 1, it's 0. You'd round all the way down to 0. It's like it's either 1,
okay.
2,
So
or
it's kind
3.
of a more. I got you. Okay.
And then
So
the one
sense.
that's interpolated is the 0.7 whatever.
That makes a lot more sense because I've seen it both, and I 0.73 is what I know as well. So I think that would be more, like you said, an approaching of a 1, but we still have a long ways to go before we become type 1.
things are accelerating. So things look bleak right now, but 100 years, look where were we 100 years ago or 200 years ago with horse-drawn buggies. Now we're like, doing all this stuff. So 1 to 300 years maybe would be a better range to think about.
Steve, before you get to the questions, I have one from a friend of ours, and he just wants to know how far out you're able to detect exoplanets, and are there any other galaxies that we can zoom into enough to check those stars with spectrometers and the like?
Okay, so I do remember there was one article, and I talked about this on the first part of this series last time. There was one exoplanet. I don't remember its name or how it was discovered. I should have double-checked that article tonight. I'm sorry. But there is one exoplanet that I know of for sure that's in a different galaxy. And I don't know, it's not like on the other side of the universe. It's probably in our local group, relatively close by. And it was observed using gravitational lensing of a foreground galaxy cluster or something like that. So gravitational lensing is pretty cool because you can use the telescope lens of the universe on top of the ones that are made of glass that you use in your telescopes. So you can get some pretty intense magnifications there. What was the other question?
I think you answered it all in that one. When you're talking about the
so that would be the farthest you could possibly see. But Kepler was looking around 3,000 light years away, 3 to 3,500 light years from Earth, in a particular set of directions in our local neighborhood of the galaxy.
Thanks, Gray Skeptic Mac, for that question. All right, Steve.
I don't really have anything. I think we probably have enough material for another segment on this at some point. But if the students in the live chat, if you have any questions, now's the time to ask. He wasn't kidding. He will give extra credit for the people that are watching. He's not going to give you an A. You have to earn that. But I'm sure he'll give you some extra credit, he said. But get your questions in now. That's all I got.
Pop quiz them.
Pop quiz. You want to do a pop quiz for your students real quick? You want like something simple?
About exoplanets?
Yeah, well, what you've just discussed.
Yeah, okay. All right, yeah.
Go ahead.
All right, pop quiz. Okay, pop quiz. Would you be more likely to find a planet around an O star or an M star? That's multiple choice. Two possible choices. Are they typing the answers in?
We're on a little bit of a delay.
Wait, do you really consider a binary choice multiple choice? I mean, if you have a choice, you have to have at least two options anyways, right? I mean, that's
so it's either an O or an M. So that's 50-50. Right?
You got two choices, so it's a multiple choice. Okay.
Multiple technically is more than one. Technically,
technically, yes. I mean, but
you're splitting hairs, I imagine. But hey,
have you met me?
That's what he does. You want to know how you want to know how you stop that? Just flick him off. And appeal to the audience, the people of reason that are watching. Usually they're in your corner.
Of reason. Did they get the right answer though?
Yeah, they got the right answer.
Yes, they're all saying M.
Good, awesome.
Yep.
Okay.
And they're rooting you on. Most of them say, "Hey, how are you doing?" That sort of thing. So
cool.
they're proud of their teacher, I think.
Yeah, sure.
Can I do a pop quiz? Which law would we use if we have the period of a planet around its parent star? What law would we use to figure out how far away it is from the parent star?
Good question. Good one. Let's see, because I mentioned that earlier.
That's a little bit more difficult, but I think they can.
Yeah,
do it.
Your next question, to tag in on that, would be: is the flat? This would be a good indicator of what type of teacher that Dr. Croon is. So, is the Earth
let
flat?
us know if he ever teaches any others flat, because then we have words. We're gonna have words with him. I might as well throw this out. I'm going to throw this out there. If Dr. Croon doesn't mind, about him wanting to engage with a flat earther. Do you mind if I throw that out there?
Sure, go for it.
Okay, so we're fishing. If you guys, we're fishing. He actually wants to have a conversation with a flat earther. So I don't want to do like the usual crowd. I don't want to do like the ones we've had on multiple times. We're looking for something a little bit different, I think. And so, if you're a true flat earther, or you know somebody who is a true flat earther, I don't want to do a Poe. That maybe even be like something who knows about physics or something would be great. I haven't met one that really does, but if you can find one. But if you know a flat earther, let us know, because we are trying to arrange a discussion between him and a flat earther.
Have you ever heard of Gavin Dale, Dr. Croon? Gav has a degree from a accredited university, and I think that would be more.
I'd be willing to do that one. Yeah, I would be willing to do that one, actually. Wouldn't end well, but I don't think his students got it. Fred got it. He's not a student. Fred, you don't count. You're not in his class. So they didn't remember this one. But Fred, you got it right.
Look,
yes, Kepler's law.
Guys, by the way, so I would debate a flat earther, but not if it's like, I wouldn't want to. So like it would be like a more casual, like a hangout, or so not like
not a debate.
Like,
You can't debate. Yeah. Listen, you cannot debate flat Earth. We call it that colloquially, but there is no debate on flat Earth. It's not flat. No done. Debate, period. Yeah. It's no debate to be had. Yeah. So
I still haven't heard a single piece of evidence in favor, like positive. I haven't heard a single piece.
You never will.
You never will. And same thing with young Earth creationism. I've been asking for a decade now, for about long before I even came on YouTube. When I was on AOL, I was talking about young Earth creationism. Show me a positive piece of evidence that is verifiable that indicates the Earth is young, or the universe. Never, not once.
Nothing. Yeah.
Right. Well, we will try to set that up. Okay, Dr. Croon, this is now your I guess your, what they used to call that, swan song, your farewell, your until next time. However, if you want to wrap up any thoughts that you have,
yeah, he's coming back.
Yeah,
you make it sound like
they can find out more about you and what you do. A message to your students. Why are they up so late? That sort of thing. The floor is yours.
Well, my message to my students is I'll see you tomorrow, and read the chapters that I signed the last week. Come up with questions. I want everybody, including and especially my students, but everybody, to realize that physics is not a course that you take. Sure, it's that too, but physics is so much more. It's a way of thinking. It's a body of knowledge. It's a way of understanding the world around us. It's a methodology. It's a way of solving problems. It's a beautiful thing, and the amount of stuff we've learned thus far, considering our small beginnings, is nothing short of amazing. And we're only going to keep increasing our knowledge and skill set from here. Just see how much we know about, even already, how much we know about these planets that are thousands of light years away. And a light year, 6 trillion miles. We never once went there and stuck a thermometer into it and measured its temperature. It's all from the power of physics and the information encoded on light that we receive and analyze with a keen caution and an informed sense of awareness of the way the universe works at these levels. I guess you could subscribe to my channel. I don't have like any real videos up yet, just some random stuff. But I am going to be changing that. I'm going to start coming out with some substantive videos this fall. So stay tuned for those, and I look forward to seeing you guys next time on the NonSequitur Show. Oh yeah.
And I just had a really cool idea that maybe you can take and think about. It would be really cool if at some point, maybe not this semester because I know that you're probably slammed, but this school year, if maybe we could do an experiment like with your class that would demonstrate that the Earth is round, and do it for one of our flat Earth shows. You know what I'm saying? Like we could have your class either brainstorm together, or as a class as a whole do something that would show either the curvature of the Earth or anything like that. That would be it would work for them, and it would be really cool to kind of highlight that on the show.
Yeah, that's
Steven.
a really cool idea. Yeah.
Real quick before we end this, people do want to continue this dialogue. They're more than welcome to, because some people have mentioned they want to go to the Discord. I have all the links now in the video description. So if you refresh after this is over, you'll get the Discord link. And right now, I guess a bunch of people want to continue this discussion over in our NonSequitur Show Discord. By all means, I'll try to pop in, but I do have some things taken care of. But we are going to have a rum and coke night tonight on my channel. If you guys want to like come over, not your students, but the adults, rum and coke night. But the links are in the video description for the Discord. So
Cool.
And I would like to take a second out real quick to thank a patron, and actually two patrons. Lysandring, you know, we love you. Thank you for your support. And David Street, who recently joined up for the highest tier. Thank you very much for your support. We really appreciate it. And I'd also like to say a quick message to Enoch Powell. Enoch contacted me today. He left a message or a comment under one of the videos saying that he normally watches the show live. He hasn't been able to do that as of late because he's recovering from an accident, and I want to just tell him that we wish him a speedy recovery and hope that you get back with us ASAP, and we wish you well. So for all of us here at Non Sequitur, I'm Kyle Curtis.
and I'm Steve McRae.
And that was John Croon, and we'll see you tomorrow at 8.
Non sequitur. Your facts are uncoordinated.